It's 1940. A phone rings in the middle of the night. A young physicist named Richard Feynman picks up half asleep, and on the other end is his professor, John Wheeler, practically shouting. Wheeler says he's figured it out. He knows why every single electron in the universe has the exact same mass, the exact same charge. Not almost the same, not approximately the same, identical, down to the last decimal. And his explanation is so strange that Feynman almost hung up thinking it was a joke. Wheeler says there's only one electron, one in the entire universe. And what looks like billions of trillions of separate electrons is actually that one single electron weaving back and forth through time like a thread being stitched through fabric, appearing over and over again, everywhere, all at once. Stay with me, because by the end of this you're going to look at your own hand differently, because every electron in it might be a memory of the same particle passing through this exact moment, over and over and over, since the beginning of time itself. Here's the problem Wheeler was trying to solve. If you've ever looked at a periodic table, you know electrons are supposed to be basic building blocks, tiny, simple, identical particles. But identical is a strange word in physics. Two rocks are never truly identical. Zoom in far enough and you'll find scratches, weight differences, tiny imperfections. But electrons aren't like that. An electron pulled from a wire in Tokyo has the exact same charge as one pulled from a wire in New York. Not similar, not close, the same, to every decimal point we've ever measured. Scientists have spent decades trying to explain why nature would mass-produce identical copies of anything with such insane precision. Wheeler's answer skipped the mass production idea entirely. His answer was, what if there's no factory making electrons at all? What if there's only ever been one? Now here's where it gets weird, and where you need to picture something most people have never actually pictured correctly. Imagine time isn't just something that moves forward, like a river you're floating down. Imagine it's more like a long hallway, and you can walk both directions in it. Normal particles, as far as we experience them, only walk forward, but in the math of quantum physics, specifically in a framework Feynman helped build called quantum electrodynamics, there's nothing stopping a particle from being described as moving backward through that hallway. And here's the twist that makes this whole idea click. When you take an electron and you flip its direction in time, mathematically, it doesn't look like an electron moving backward. It looks exactly like a completely different particle moving forward, a particle called a positron, the antimatter twin of the electron, same mass, opposite charge. And normally we think of these as two separate things. Feynman and Wheeler realized the math didn't care whether it was two separate particles or one particle doing a U-turn in time. So picture this. One single electron exists. It moves forward through time for a while. Then something happens. It collides. It interacts. And in the math, it appears to reverse. It starts moving backward through time. But from our point of view, watching things only happen in forward order. That backward-moving electron looks like a brand new particle, a positron popping into existence and zipping off into the universe. Then later, that positron hits something else, flips again, and becomes a forward-moving electron again. Over and over. Forward, flip, backward, flip, forward again. Like a single ball bouncing between two mirrors positioned at either end of time itself. And every single bounce where it changes direction, looks to us like the birth of a brand new particle. Now here's the part that made Feynman go quiet on that late night call before he started laughing. If this one electron has been bouncing back and forth since the beginning of the universe, then every electron you've ever heard of, in every atom, in every star, in your own body right now, could all be the same particle, not copies, not clones. The literal same object, appearing at countless points in space-time because it's zigzagging through the fourth dimension, so many times that from our slice of now, it looks like trillions of separate electrons exist simultaneously. It's like if you had one strand of thread and you stitched it through a piece of fabric 1 billion times. If you were an ant living inside that fabric, only able to see one layer at a time, you'd think there were 1 billion separate threads. You'd never guess it was actually one continuous strand weaving through, disappearing and reappearing. Let's pause here, because your brain probably just tried to break this into something familiar, and I want to stop you before it does, because the real version is weirder than the simplified version. This is not multiverse stuff. This is not parallel universes. This is one timeline, one universe, one electron, allegedly, doing an absurd amount of time travel within it. And the reason this idea survived long enough to become a real footnote in physics history, instead of getting laughed out of the room, is because the math actually works. Feynman used this backward in time trick, this positron equals electron moving backward idea, as a real calculational tool in quantum electrodynamics, the theory that eventually won him the Nobel Prize. He didn't necessarily believe, literally, that there's one electron bouncing across all of time. But he took the idea seriously enough to build diagrams around it. Feynman diagrams. The exact diagrams physicists still use today to calculate particle interactions, where an arrow pointing backward in time is treated as a particle of antimatter moving forward. That's not a cute analogy. That's literally baked into the notation physicists use every single day. So why doesn't every physicist believe there's truly one electron? Here's the twist. Here's the reset moment. Because there's a problem with Wheeler's idea, and it's a big one. If it's really the same electron bouncing back and forth billions of times, there's a number problem. In the observable universe, there are vastly more electrons than positrons. If they're the same particle taking turns, forward, backward, you'd expect roughly equal amounts of each, because every backward bounce should create one visible positron for every forward stretch that creates a visible electron. But that's not what we see. Electrons dominate. Positrons are rare, and when they do show up, they usually annihilate almost instantly when they touch matter. Feynman himself brought this exact problem up. He asked Wheeler on that phone call, "But then where are all the positrons?" And Wheeler, without missing a beat, apparently answered, "Perhaps they're hidden in the protons," which is, honestly, one of the greatest deflections in the history of science, because nobody has ever proven that, and most physicists today think the one-electron idea, while beautiful, doesn't match how many particles we actually observe. But here's why this story refuses to die, why physicists still bring it up at conferences, why it still shows up in Feynman's own Nobel lecture decades later. Even if the literal version isn't true, the concept inside it changed how physics is done. The idea that antimatter can be mathematically treated as ordinary matter moving backward through time isn't a fringe theory anymore. It's standard. It's taught. It's used to predict real experimental results in particle accelerators. So in a strange way, Wheeler was wrong about the literal claim, one electron doing all the work, but he stumbled onto something true hiding inside the wrong idea. Time, in the world of subatomic particles, might not be as one-directional as it feels to us. Particles genuinely behave, mathematically, as if the past and future are just two directions you can travel, not a one-way street. Here's where it gets almost uncomfortable to think about. If a single particle can be described as moving backward through time under the right mathematical conditions, what does that say about causality at the smallest scales of reality? What does it mean that the universe's laws don't actually forbid time reversal at the particle level? They only look forbidden to us because of how entropy and probability stack up at large scales. The one-electron universe theory might be wrong as a head count, but it cracked open a door that's never really closed since. A door that says, maybe the reason time only seems to move forward for us, for humans, for stars, for everything we can observe with our eyes, is a statistical illusion built from trillions of particles, all agreeing to move the same direction, even though nothing at the fundamental level actually demands they do. So next time you touch something, a table, your phone, another person's hand, remember this. The electrons buzzing in the outer edges of every atom in that object are, according to the math physicists still use every day, indistinguishable from a single particle that might be bouncing backward and forward through time trillions of times a second. Whether or not it's literally one electron doesn't even matter anymore. What matters is that for one wild night in the 1940s, two of the greatest minds in physics looked at the universe and asked, what if everything we call many is actually just one, moving so fast through a dimension we can't perceive that it only looks like many? And nobody has ever fully closed that door. If this messed with your head a little, that's the whole point of this channel. We take the strangest, most mind-bending ideas in physics and break them down without the boring textbook language. If you want more of this, hit subscribe, drop a comment telling me what universe-breaking idea you want explained next, and I'll see you in the next one.